In this section, we will discuss the performance analysis of square wave inverters. Last session, we were discussing about a single phase half bridge inverter and full bridge inverter. And single phase full bridge inverters. Both this will come under square wave inverters because its output is square wave. Output voltage we are getting is a square wave. So let us draw the output voltage waveform. This was our output voltage waveform of a half bridge as well as full bridge inverter. The thing is, for half bridge, the maximum positive voltage amplitude will be Vs by 2, whereas it is Vs for full bridge inverter. So let us T by 2, this be T. This is Vs and this is minus Vs. This is for a full bridge inverter. Single phase. The output voltage waveform. Okay. This is here V0. Okay. So let us take the Fourier analysis of this. You know that this waveform will be having, it is having odd symmetry. So A0, AN will be absent. Taking Fourier analysis. We are going to write the Fourier series expansion. So only Bn terms will be present, and this, as we look into the waveform, we can see that it is having half wave symmetry. So the even harmonics will be absent. As it is having even harmonics will also be absent because of its half wave symmetry. And the general expression for Fourier series for the given waveform, this output voltage waveform, we can express it as a Fourier series as V0 of t is equal to V0 by 2 plus sigma n equal to 1 to infinity an cos n omega t plus bn sin n omega t. Where an is given by 1 by pi integral minus pi to pi f of t cos n omega t d omega t. Where n is equal to 1, 2, 3, etc. in general. And Bn is equal to 1 by pi integral minus pi to pi, or else we can take it as 0 to 2 pi. f of t, the function, multiplied by sine n omega t d omega t. 4n is equal to 1, 2, 3, etc. And in this case, in our case, as the function is an odd function and a half-wave symmetry is there, a0, an terms will be absent, and we need to calculate only bn. And that bn, of course, the even harmonics will not be there. So we can try to write in this case what is bn. So bn is equal to 1 by pi integral minus pi to pi. That function we can write it as instead of 1 minus pi to pi, let us consider divide it into two segments like minus pi to 0 and 0 to pi. If we extend this backwards, the waveform will be like this, no? So minus, this will be your, this is your pi, and this is 2 pi, this is 0, and this will be minus pi. So the waveform goes like this. So minus pi to 0, the function is minus Vs. So we can write minus pi to 0 minus Vs into sine n omega t d omega t plus integral 0 to pi Vs sine n omega t d omega t. So that is equal to that's equal to 1 by pi into this will be Vs, we can take it outside, so it will be Vs divided by pi. Okay, Vs by pi, and integral minus sine n omega t, you will get it as minus cos omega t. So sine n omega t, the integral will be minus cos omega t. So it will be cos n omega t divided by n, no? So that within limits minus pi to 0, that plus Vs is taken outside, sine n omega t, it will be minus cos n omega t by n, and that too within limits 0 to pi. This is equal to Vs by n pi. I have taken n also outside, so it will be in bracket, it is cos 0 minus cos n pi. It will be minus cos of minus n pi, it will be minus cos n pi itself. So cos n pi, cos of minus theta, cos theta. No? So cos n pi, then minus cos n pi minus minus. So it is plus cos 0. So it will be cos 0 is 1. So Vs by n pi into 1 plus 1, 2 minus cos 2 cos n pi. So 2 into 1 minus cos n pi it will be. So it will be 2 Vs by n pi into 1 minus cos n pi. And this is n is equal to, as even harmonics are absent, we can write n is equal to 1, 3, 5, etc. Okay. And this, we know that this cos n pi, this term will be equal to minus 1 for all n equal to 1, 3, 5, etc. So it will be 1 minus 1, no. So it will be 2. So 2 into 2, 4 Vs by n pi. It will be Bn will be. And the Fourier series expansion, we can write it as V0 of t, which is equal to sigma n equal to 1, 3, 5, etc. up to infinity. Bn it is 4 Vs by n pi into sine n omega t. This is 4 n equal to 1, 3, 5, etc. up to infinity. This is 4 full wave, full bridge inverter. For single phase full bridge inverter. And for half bridge inverter, Vs, instead of Vs, it will be Vs by 2. So for half bridge inverter, half bridge that is single phase, we can write it as Bn is equal to 2 Vs by n pi, it will be, and V0 of t, we can write as a Fourier series as sigma n equal to 1, 3, 5, etc. up to infinity, 2 Vs by n pi sine n omega t. For n is only odd harmonics will be there, 1, 3, 5, etc. Okay, up to infinity. And this function V0 of t will be equal to 0 for 2, 4, 6, n is equal to, for n equal to 2, 4, 6, etc. It is only odd harmonics will be present. This is for half bridge. Now we'll see what is the RMS value of nth component. The RMS value of nth component, we can, of output voltage. That's for a full bridge. We can write it as Vn, which is equal to, Vn is nothing but, this is the amplitude of the nth harmonic, 2 Vs by, 4 Vs by n pi. Okay, so that amplitude maximum value divided by root 2 will give you the RMS value. So maximum value is given by 4 Vs by n pi. So n pi, the whole thing divided by root 2. So 4 Vs by n pi root 2 it will come. Means 4 by root 2 pi. 4 by root 2 pi will come to 0.9. So 0.9 times Vs by n. For n is equal to 1, 3, 5, etc. Okay. So that is the RMS value of nth component. So so the fundamental component will be putting n is equal to 1. Okay, fundamental component, the RMS value you'll get it by putting n is equal to 1. So it will be 0.9 Vs. And for half bridge, This will be Vn will be equal to 2 Vs by n pi root 2. So it will be 0.45 Vs. 0.45 Vs divided by n, sorry, Vn. Okay, and V1 will be 0.45 Vs, the fundamental component. Now, we'll discuss the performance indices. The first performance indices is harmonic factor of nth harmonic. It is the harmonic factor of nth harmonic. So that is given by harmonic factor of nth harmonic. Harmonic factor is a measure of the individual harmonic contribution in the output voltage of an inverter. It can be defined as HFN, which is equal to Vn by V1. Where Vn is the RMS value of the nth harmonic component and V1 is the RMS value of the fundamental component of output voltage. Next term is the total harmonic distortion, THD. Distortion, THD. THD, it is defined as the ratio of RMS value of total harmonic component of output voltage and the RMS value of fundamental component. It's the ratio of RMS value of total harmonic component of output voltage to that of the RMS value of the fundamental component. It actually gives gives a measure of how close the shape between the output voltage waveform and its fundamental component. So it is a measure of closeness in a shape between the output voltage and its fundamental component. So mathematically we can express THD as THD is equal to root of sigma n equal to 2, 3, 4, etc. up to infinity Vn square. So that is the harmonic components divided by the fundamental component of RMS value. RMS value of the fundamental component, that is V1. So this can also be written as square root of VRMS square VRMS square minus V1 square. That will give you the harmonic components. So that minus V1 square divided by V1. So VRMS is the RMS value of the output voltage and V1 is the RMS value of the fundamental component. Next term is the total distortion factor. So distortion factor, which we can write it as, we will also represent it as distortion factor DF, which indicates the amount of harmonics that remain in the output voltage waveform after the waveform has been subjected to second order attenuation, or else it can be said that it is divided by n square. So mathematically we can express distortion factor as equal to root of sigma n equal to 2, 3, etc. up to infinity Vn divided by n square, this whole square, because it is within roots. So that divided by V1. So for the nth harmonic, we can say distortion factor for the nth harmonic, distortion factor n, which is equal to Vn divided by n square V1. Then last performance indices normally we use is the lowest order harmonics. Lowest order harmonics. Lowest order harmonics. It is the lowest frequency harmonic with a magnitude greater than or equal to 3% of the magnitude of fundamental component, which is defined as the lowest order harmonic. If the low, it simply shows that if the frequency of the LOH is higher, distortion of current waveform is lower. Okay, so we continue to analyze these parameters for our square wave inverter spectrum. So HFN is equal to, we have seen that HFN, harmonic factor, HFN is Vn by V1, no? So what is Vn actually? For square wave inverters. HFN is nothing but Vn by V1, and you know that Vn is equal to 4 Vs by n pi root 2 for full bridge and 2 Vs by n pi root 2 for half bridge, and that divided by V1. V1 is 4 Vs by 2 root 2 pi. No. So it will be, once we divide Vn by V1, we'll get it as 1 by n. That is 4 n equal to 3, 5, 7, etc. Okay. So while putting the different n values, you can write it as HF3 is equal to 1 by 3, which is 0.33, 33.3% of the fundamental component. That's the meaning. So HF5 will be 1 by 5, no? So it will be 0.20. HF7, 1 by 7, it will be 0.143. HF9, it will be 1 by 9, no? So that will be 0.111. And HF11 will be 1 by 11. That will be 0.091. Now it is around 9.1%. So this simply shows the amplitude of the harmonic component present in that. So if we plot this spectrum of a square wave inverter, we'll get it as, if this is the fundamental component, if this much is the fundamental component, the third component will be 1/3 of that, no? Third frequency component will be only 1/3 of that. This is for the third frequency, third harmonic, and 1 by 5th will be the 5th harmonic, 1 by 7th will be the 7th harmonic, and 9th, 11th, like that it goes. Okay, etc. Now we will try to find the THD for a square wave inverter. You know that for full bridge inverter, Vrms will be equal to Vs, and V1 will be equal to Vn when n is 1. No, Vn is actually, we'll write Vn first. Vn for a full bridge inverter, it is 4 Vs by n pi root 2. And that was actually 0.9 Vs by n. So V1 is 0.9 Vs. So for full bridge inverter, we can write THD is nothing but a root of THD was equation for THD was root of Vrms square minus V1 square all divided by V1. So this will be Vrms is simply Vs itself. So Vs square minus V1 was 0.9 Vs. So that square within square root. So that divided by V1 itself. V1 is 0.9 Vs. So you will get this as 1 minus 0.9 square. No, it is root of that divided by 0.9. It will be 0.4834. So THD, you'll be getting it as 0.4834. Okay. Now we will check the THD for a half bridge inverter. For half bridge inverter, what is the RMS value of output voltage? It's a square wave with the amplitude Vs by 2. So that is Vs by 2 is the Vrms, and Vn was 2 Vs by, here instead of 4, here it was 4 Vs by n pi root 2, here it will be 2 Vs by n pi root 2, that will be equal to 0.45 Vs by n. And V1, the fundamental component will be, V1 will be equal to 0.45 Vs. So substituting on the THD equation, we'll get it as THD is equal to Vrms is Vs by 2 whole square minus 0.45 Vs the whole square within roots divided by 0.45 Vs. So it will be 1 by 2 whole square means 0.25 minus 0.45 square divided by this much within limits, that into Vs divided by 0.45 Vs. So you'll get it as same as, you get it as 0.4834 itself. So THD is the same for a full bridge as well as a half bridge inverter, or 48.35%. Okay.